Thank you, everybody. I'm Jeff Milner. I work for the Public Education Foundation. I always come up here and ask y'all for stuff. This is not different. Next week is Computer Science Education Week. We're working with the district to try and get 20,000 kids to go through the hour of code or spend an hour on someone else's sort of programming tools and just to expose as many kids as possible as we and the district work to build the support so it's not just an hour a year or after school or during the summer. It's a small ask if you're interested. Code.org/volunteer. You can just put in kind of where you would, the kinds of things you might be interested in volunteering for. A lot of it's just Skyping in for 15 minutes and talking about what it is that you do in your job. But we're pointing teachers and educators who are not experts in programming but are experts in teaching and opening doors for their students to use the code.org resources to get connected with some of the awesome professionals that make the developer community here and technology community here in Chattanooga so different. So if you're interested and might have some free time next week during CS Ed Week, code.org/volunteer and get registered. Thank y'all, I appreciate it.
All right. What was the web address again? Code.org/volunteer. All right. So you heard it here, folks. All right. Anybody else want to make a shout out for an event that you might have? Yes? No? Okay. Well, without further ado, we have Crypto 102 with Aram. So, Aram?
Aram, yeah.
My bad. Everybody give it up for Aram.
Thank you. It's a pleasure to be here again. I'm going to go, some of you were here at my first presentation, my intro to crypto or Crypto 101. Then I'm going to talk a little bit, go into a little bit more details about DiffieHellman and RSA. I had hoped to put in elliptic curve, but I ran out of time. Even though Brett and I have been talking about this for almost 2 months. I was up last night, still working on the presentation. And then I'm going to talk about authentication versus authorization, which is something that gets confused, and it's part of security. So for those of you that didn't see my original presentation, there's a YouTube here, and I was going to ask Brett if he got authorization for me to post it there, but we'll see. So cryptology is the science of secure communications. Cryptography is a branch of cryptology that designs algorithm for secure communications. And in the US, cryptography and cryptology tend to be used interchangeably. Cryptanalysis is the branch of cryptology that tries to break things. So, find ways to break the encryption and decryption. Encryption is basically just a mechanism used to provide the confidentiality. And it's usually done by encrypting a message, and you decrypt to unscramble the message. At any time, feel free to ask questions. A cipher is just another name for an algorithm that does encryption. Your plain text is what's the message that you're trying to securely communicate. And ciphertext is basically that message encrypted. And in security, cryptography, there's two parties generally referred to as Alice and Bob. And they're trying to securely communicate. A critical thing in modern security, although this Kirchhoff was back in the 1800s. He came out with this rule or principle that the security of your system should only depend on the secrecy of the key, not the secrecy of the algorithm, which leads to this security through obscurity, which is the fallacy of thinking that if you keep your algorithm secret, no one can break your security system. Anybody here use Linux and you watch DVDs on Linux? Well, the DVD people thought that by keeping their algorithm secret, they could protect DVDs. And that's why, you know, I think it was a 13-year-old kid wanted to, you know, watch his DVDs on his Linux machine and reversed engineer the algorithm and, you know, published it. So if you're designing anything secure, remember that assume that your attacker knows everything, and the only thing you want to protect is the key. So encryption, you know, takes your plain text, you run it through some function, you have an encryption key, and out comes a ciphertext, which can go over a non-secure environment. And decryption basically takes your ciphertext, runs it through some function with a decryption key, and out comes a plain text. Until the mid-70s, all crypto systems were based on what's called a secret key. And in these secret key crypto systems, the key used to encrypt is the same key used to decrypt. So what that meant is that two parties needed to know that key. Because you had to, you know, to decrypt, you had to have the key used to encrypt. In the mid-70s, maybe a little bit earlier, well, in the mid-70s, it was publicly announced a public key crypto system, in which case the key used to encrypt is different than the key used to decrypt. And we'll talk about those. Secret key crypto systems are generally quite fast and easy to implement in hardware. Public keys are based on advanced mathematics, and so are generally hard to implement in hardware. You know, we still don't have very good multipliers and dividers in hardware. And because of the way of these, the math, they're generally slow in software. So the first public key system that was made was by Whitfield Diffie and Marty Hellman. And they wrote this paper called New Directions in Cryptography in 1976. And this was basically the first public presentation of this concept. It turns out that GHQC, or it's basically the British NSA, had some mathematicians that actually had discovered this principle, but because it was classified, it wasn't publicly released. And the DiffieHellman, it's called a key exchange algorithm. The security is based on this apparent difficulty of computing logarithms over a finite field with a prime number of elements. And I'm not a mathematician. I think you're studying math. Okay. And in their paper, they sort of define, give this definition of what a public key crypto system. And again, I'm not a mathematician, nor a cryptographer. So you can read this, and I'll post this presentation on the meetup. And again, so both DiffieHellman and RSA depend. What makes it difficult is this mod operator. Anybody know what mod or modular math is? Everybody? Right, it's the remainder. It's the reason why if it's 11 o'clock, and I tell you let's meet in 3 hours, we don't meet in 1400. Well, unless you're in the military, we meet at 2. Okay. So this is the basic equation used for DiffieHellman. So Alice and Bob want to communicate, and the first thing they do is agree on this P number and this G, and G has to be a primitive root modulo of P. And I don't understand exactly what that means other than, you know, it's some root modulo your P. So they have to agree on this beforehand, and those numbers are public. So Alice picks a secret integer called A, and she sends Bob this message A that's defined to be as G raised to the A power mod P. So if she picked 3, you raise 3 to the 3rd power, which is G. Here, modulo 17, and you get 10. And then Bob does a similar thing, picks a B and sends it to her. So in this case, he picked 11, so you run the math and you get 7. And you know, this A and this B is sent over an insecure channel. It doesn't matter if someone listens on that communications. When Alice gets B, she does this function here. If you look here, she ends up with 3. Bob does similar thing with the A he received from Alice, and lo and behold, you both get the same number, which is a secret key. So someone looking at that communications, because of this difficulty of this log, finding out the log, can't figure out that number. And once Alice and Bob have this shared secret, now they can use that shared secret generally to generate a symmetric or a secret key and use that to encrypt your messages. Shortly after DiffieHellman published her paper, 3 professors at MIT liked the concept and wanted to come up with a true public key encryption system. Again, DiffieHellman is key exchange. And there are some crypto systems based on DiffieHellman, but they came later. But DiffieHellman and RSA are sort of the 2 popular encryption algorithms. Elliptic curve cryptography is similar to DiffieHellman, except using elliptic curves. And again, I ran out of time to put some slides together on it. But they published their paper in 1977, and in their, the basis of the security is again this presumed difficulty of factoring the product of 2 large prime numbers. So if someone ever, comes up with a new algorithm for factoring numbers, then RSA will be broken. And MIT was granted a patent in 1988 or 83 because they had published in 1977 the description. They weren't able to get a world patent, so RSA was only patented in the U.S. Other, anyone outside the U.S. could use RSA. Anybody here heard of PGP? Okay, so PGP, although it was started here in the U.S., sort of, they did things outside the U.S. to get it, so it was used a lot outside the U.S. So the basic equation is you have a message, you raise it to two exponents, and then you do the mod n. So you can call this encryption and this decryption. Your public key is basically this N and this E, and the private key is D. Again, that has to be kept secret. So Bob wants to send a secure message to Alice. So what Alice does to create her public key is she chooses two prime numbers. In this case, we're picking very small numbers. Nowadays, you want to pick at least a 2048-bit public key, and preferably a 4096. I don't know why they double. They use a power of 2 for these key sizes. But I pick small numbers so you can sort of do this in your head. Alice then computes this, called the Euler's Totient function. I cheated. I used Wolfram to calculate this. But there's algorithms for coming up with this. So if n, which is the product of these two primes, is 143, then this totient of n is 120. And then you choose an arbitrary number again, where it has to be greater than or less than this n. And then you have to find this number d, which is the inverse of E mod this totient, in which case we come up with 103. And now Alice's public key is N, which is 143, and E, which is 7. Bob wants to send this message. Again, for conciseness, I picked 1. Let's think of this as 1 if by sea, 2 is by land. So you convert M into a number. So 31 is the ASCII value of 1. And then to get your ciphertext, you take M, or 31, you raise it to 7th, which is part of the public key, and then you do the modular 143, and you get 125. So when Alice gets this number 125, she takes it, does this inverse, and she gets back 31. So again, you can send this over insecure channel, and only Alice knows this number here so she can decrypt. Let's switch gears a little bit. Again, this is part of security, and let's talk about authentication versus authorization. So authentication is the process of verifying the identity of an object. And generally, we're trying to authenticate either a person or it could be a machine. When you go to Amazon and you put in your credit card number, you want to make sure you're talking to Amazon. And the process is based on using one or more of these following factors. One is what you know, or what you have, or what you are. And it's logical that the more factors you use, the better your authentication and the better your security. So what you know is basically some secret. What you have is something you carry with you. I don't know, any of you use PayPal? PayPal will send you this. So it generates a number, so when I'm going to pay with PayPal, if I don't have this, I got to go through some hoops to authorize that payment. There's also, and I didn't get a chance to talk about this, but there's a standard for the internet called FIDO, and I forget what it stands for, but you can buy these little USB tokens. This is around $10, $15. There's some, you can pay more for some more advanced ones, but there's certain websites that I go to that it asks me to stick this in, and they do some sort of challenge response based on this. On here, you can, a token, token, instead of something physical like this, it can be an app. I have something called Authenticator, something called VIP Access. I use that for my E-Trade. Authy, I forget where that comes from, and another thing called Authenticator. This one Authenticator is for GitHub, so you can set that up. And biometrics is basically something, I'm sorry, what you are is basically biometrics. So you can have your fingerprint, either retinal or something about your eye. It could be your face, voice, how you type, how you walk. When I used to work at Qualcomm, there was a group working on sort of looking at how your phone was behaving, how it was moving, and that to use as for authentication. And signatures are very common. Basically how you write. Just a side note here. A lot of people think that when you sign, your signature should look the same or similar to your previous signatures. Legally, there's no requirement to do that. That's why you can put an X and someone can sign for you, and that, no matter how many X's you put, the different people can sign for you. So what's called single factor authentication is basically just using one thing to authenticate. Everybody's familiar with passwords or passphrase. A PIN could be a government ID. Get to that. I still haven't gotten my Tennessee license. I got my California license. So for certain things, I'm authenticated by this. If you're designing something, you should limit the number of retries, and you should try to increase the time in between retries. You have a server and someone's attacking it. If you let them just repeatedly to try different passwords, that's bad. You can sort of prevent that by putting a delay that increases with the number of retries. So two-factor authentication, everybody's familiar with your ATM card, right? So, I stick this in or swipe it, and then I have to put in a PIN. And if you look how a bank does the ATM and PIN, they give you like 10 tries, because a PIN's only 4 digits. So, there's only 10,000 possible numbers. So they limit it to 10 tries, and then they lock you out. Again, having some sort of physical token. So when I log into PayPal, when I'm going to pay, I put in my password, and then it's going to ask me, I press this, gives me a digit that I have to type in. Other ways is someone will send you a code, a text to your phone. So you put in your password, then they'll send you a text that you have to also put in. Three-factor is the most secure, but very few there are very few implementations, partly because it's so cumbersome. I mean, it's bad enough, having to carry this around. And in security, there's always this trade-off between convenience and the level of security. And generally, you only see this on TV, or a movie, James Bond or Mission Impossible. There's no sort of foolproof authentication process. Anybody here ever get a fake driver's license? How many of you have ever been asked for your social security number or your card? I mean, that doesn't prove anything. And tying back into the crypto, so when you have passwords or PINs or biometrics, usually those are protected using an encryption. So you don't have to have that in plain text stored on some server. So authorization, which should come after authentication, is the process of verifying that the actions that this object wants to do are allowed. Are you permitted to do what you're asking to do? And again, if you don't do it without authorization, without authenticating, then it's basically useless. And most access control systems are based on, authenticating, then checking the authorization. And you got to remember that even if you're authorized, there may be limits. I'd love to go to the ATM, put in my card, put in my PIN number, and withdraw $1 million, but that's not going to happen. And it's critical not to confuse authentication with authorization, even though it's done a lot. My driver's license, how many of you have ever been carded? Right? Is there anything in here say that you're authorized to drink? Nothing on here that says that. And in fact, at least in California, it says this license is issued as a license to drive a motor vehicle. Does not establish eligibility for employment, voter registration, or public benefits, and they should add, or to drink. But again, we humans tend to be lazy, and you know, this has my age, and the law says you must be over a certain age to drink, so that's why bars use this. Questions? Go ahead.
Early on, you said that DiffieHellman was a key exchange, while algorithm, while RSA is an encryption algorithm. Could you elaborate on the difference between those two?
With DiffieHellman, you don't encrypt the actual data. With RSA, you can encrypt the actual, you know, if we want to exchange a message, with RSA, I can encrypt it in one process, in one step. With DiffieHellman, we would do this what's called the Diffie-Hellman key exchange. Then we would generate a symmetric key. Then I would encrypt using that symmetric key, and then send you the message. Anything else? Well, thank you.
Thanks, Aram. Appreciate it. So next week we kind of have a different change of pace. We're going to have an accountant talk with us. His office is in Florida, so it'll actually be a remote talk. And he's going to be talking about how you can successfully and more efficiently automate your various accounting processes and that kind of stuff. He's going to bring some tips to us for that kind of thing and help streamline it. So should be a very good kind of meat and potatoes talk that you can use straight away. So that'll be fun.